Okay, good morning everyone. Today we're going to talk about programmable shaders, specifically vertex shaders and fragment shaders, and I'm going to show you some examples. First, let's go over the slides quickly to give an introduction to these programmable shaders. And in the last couple of weeks, I've actually been showing you these vertex shader and programmable shader examples, which allow us to replace parts of the forward rendering pipeline with our own code that we can use. We can do some effects that are not possible in the standard pipeline. So yeah, this is where we talked about last time. Some tasks, like some of the tasks, like clipping and rasterization, are still done automatically by the forward rendering pipeline automatically in the background, but certain parts like vertex processing, multiplying your vertices with these modeling, weaving, transformation, projection matrices, or doing it in different ways, you can run your own, write your own shader to do those things. So this is what programmable shaders are. Shader, actually the term is a little bit misleading. It's like, it's just, when you hear something about a shader, you only think about coloring certain parts of the scene, but it's not only about colors. You can write shaders that change different things about the geometry of your scene. You can, for example, do interesting vertex scaling effects by changing your vertex shader. But yeah, the term just has stuck among the computer graphics programmers, so that's why we are still using. We are using this term. It refers to parts of the. It refers to modules in the forward rendering pipeline that you can change. Okay, so we can when we override a shader, we have to implement the basic things that is required from us from that module. Okay, it's a really it's a language. It's written in there are different languages that supports program that you can use to write programmable shaders. The most common one is GLSL, and if you want to see examples of fragment shaders, you may visit this site that I showed you before, which was the Shader Toy. The Shader Toy contains thousands of very nice fragment shader examples, which are really remarkable. I mean, look at this. I mean, these are, while I'm hovering my mouse on them, they are actually interactive in real time. These are not videos that we're watching. These are graphics applications, fragment shaders that run on my machine's GPU as I'm moving over them. So if you click on that, you can see the code that makes up this shader, minimum rings, maximum rings. So there are lots of parameters about what kind of animation this is like a fractal of rings. That's really nice. And as you can see, there are reflections. There are shadows. So shadows, reflections. We see the reflections of the floor on these. So it's really remarkable. I mean, how how mathematics, as you can see, this is, I think they're using quintic splines for this, and this is the to display a torus. This is maybe for shadow mapping. I'm not sure. It's just I'm just trying to guess by the name of the function here. The gradient ray marching. So it's using ray marching, which is similar to ray tracing. In which we trace arrays. So this is a different algorithm than ray tracing. This one is using, but you can actually implement a ray marching algorithm within a fragment shader, within the final fragment processing module of your application. You can actually write the entire module to create a graphics application that looks like this. And it's right now 60 frames per second. It's really high. And this is shadow trace. I think this is soft shadows. They're using not the shadow mapping algorithm, but a different algorithm that I don't know myself. Shadow trace, sky color. So sky color is just this one, a simple return some color. shading, and the main image. So, and this is, it looks very much like the C programming language, but certain types like vector tree and certain functions like normalize, cross product are built in. And finding the reflection vector, for example, there's a function which is reflect, which gets the a vector and some normal vector, and gets the reflection of this vector with respect to this normal vector. So it's really remarkable. There are really cool fragment shader examples that you can see. There are also nice tutorials on YouTube that show, I think I did, not this one, but there's a, by just using how mathematical functions, you can generate, for example, a palm tree. And by using these fragment shader built-in functions, you can create a scene, a two-dimensional scene, by just using the mathematical functions and changing the parameters of these functions. You can create really nice curved shapes and change the color of the sky, for example, to get a very nice sunset color in the background. So these are all possible with these fragment shaders. So we are going to learn a bit of this GLSL language. You can, as I said, it's very similar to C programming language, so it's not going to be like learning a completely, totally new language. All you need to do is learn some basic functions that we use, and just look at the examples that I have provided. And the programmable shaders, they are a piece of code that are compiled and linked and run on the GPU. So while the main application, which is responsible of getting the user input, keyboard, mouse input, and displaying everything on the frame buffer, the Windows operating system level interactions, they run on the CPU. The application runs on the CPU, but the fragment shade and vertex shaders, these programmable shaders, they run on our GPUs. They are used to create a variety of visual effects. For example, you can even do non-photorealistic rendering if you want to achieve like cartoon-like effect. Here there are some examples. For example, this non-photorealistic rendering fragment shader example. If you just with these keywords, there are many, there are some papers that actually, some research papers from AMD, probably there are some examples in which yeah, let's see whether there are, yeah, look at this. Cartoon shaded with outlines. And what you see here, I don't know which language, maybe it may not be written in GLSL, but you can get such effects with exact boundaries for different shaded colors, not smooth transitions at the surface. This gives like a cartoonish feeling to whatever we render. And look at this. This is the Utah teapot, the famous Utah teapot, one of the first objects that are rendered by three-dimensional computer graphics applications. And it really looks like an hand-drawn object, although it's also computer-generated. So there are different, I don't know, yeah, look at this, really, it's like sketched by hand. This is, again, computer graphics generated application image, but I mean, this is CGI, but it looks like it's hand-drawn. So this is called non-photorealism, non-photorealistic rendering, and you can see examples of that, and you can do such things with the help of programmable shaders. So it's one of the visual effects programmable shaders allow us to do. Yeah, there's an example here on our slide as well. This is some Microsoft's XNA game platforms demonstration, and here are some program demonstration by NVIDIA and AMD, which uses programmable shaders. So what are we targeting with programmable shaders? Usually there are two programmable shaders we are going to be writing, vertex shaders and fragment shaders. There are also other shaders that you can write, for example, tessellation shaders, which allow you to generate a kind of a triangulation given a set of point clouds. Your vertices may be points. You may not have triangles defined yet, but you can define your triangles on your own by using tessellation shaders, or there are also geometry shaders. There are different other shaders, parts of the pipeline that you can override as well, but the most important ones are these vertex and fragment shaders. And just how important this fragment shader is, this shader toy contains entirely fragment shader examples. These are not, when you click on something, what you see here on the right here is actually the fragment shader, which gives the final color. This frag color is the final output of a fragment shader, which computes the color of a single pixel. So what you see here, the entire code you see here, is a code to generate the color of a single pixel, a single fragment. And this is run in parallel. So this is so fast because it runs in parallel for all fragments by using the multiple cores on our GPU. And again, how this shows, I mean, this is really mathematics joining with art. I mean, mathematics producing these nice artistic imagery. These are really nice examples. So how do we rotate the joint, draw joint, endpoint? So this is like this arm here has a number of joints, discrete joints, and how I think probably they have some kind of a inverse kinematics type of application here. In inverse kinematics in robotics, for example, there's a target. This is like the end effector where you're and this. So what should be the angles of these joints so that the end effector is as close as possible maybe to this target. But this is the area of robotics, so I'm not going to delve into that. So let's go again. There are thousands of examples you can get inspired from this shader toy. So vertex shaders, the code that you write are run in parallel for the vertex data that you send to the GPU. So whatever our vertex array contains vertex buffer objects, the vertex processing, the vertex shader deals with what happens to these vertices. Are there attributes associated with these vertices? So it runs in parallel, so you write code basically for a vertex of a triangle. So for each of these vertex, the code you write, it's for a single specific vertex. Fragment shaders are code that are written for fragments of primitives, like a fragment of a triangle like this, is basically the code you write for a pixel, or potential pixel, if it's not overwritten, or if it's not occluded by another object behind. So each vertex is passed to the vertex shader. As the vertices are processed, we rasterize polygons. The rasterization is done automatically in the background. Anything you have variable attributes for vertices you have, they are automatically interpolated for the primitive, like this triangle. Position, color, depth, all these things are interpolated across the polygon, and the interpolated values, all the interpolated values are passed automatically to the fragment shader as input. Fragment shader gets the coordinate, XYZ coordinate of this part of the triangle. It gets the color, depth, everything we can give to the fragment shader. We will be writing for this particular pixel or fragment. What can we do? What are the things we can do in a shader? For vertices, vertex processing, we can do vertex transformation. We can have some associated properties, attributes with vertices like the normal vectors. We can transform our normal vectors. There can be assigned texture coordinates for that vertex. So we can assign texture coordinates to vertices. We can transform texture coordinates. We can perform, if you want to do lighting computations per vertex, and then use interpolated color values for fragment shaders, we can do per vertex lighting. This is also called Gouraud shading in default OpenGL, and this is what it is done by default if you don't have any programmable shaders, or if you're using the default program. By the way, every time in an OpenGL application, on the CPU side in an OpenGL program, by using GL use program, or I think it should be GL use program, or let me see whether the function is. I have examples here. In this one, in this first examples, there's a very not this is the second one. In the first examples, there's a really advanced this depth as texture, also this terrain visibility. These are really advanced examples, and this depth. There, as you can see, there are two types of shaders here. Two shaders here. The simple one and the depth shader. If you look at this code, it's much longer than the other examples, but it's still like 600 lines. There should be GL use program call here. Yeah. So this is the function which tells you may have multiple shaders attached together inside a program. A program refers to the entire set of shaders that make up a pipeline. So you have vertex shaders, you have fragment shaders, you compile them, link them, and then you attach them to a program. Program in this context refers to this the pipeline, the entire pipeline. So when you may have multiple different vertex shaders linked and attached to different programs, and you can switch between those programs while you are running your application. And in this case, when you say GL use program, where did I write that here? Yeah, when you say GL use program 0, 0 always refers to the default pipeline with no user-defined programmable shaders. Okay, so GL use program always reverts back to the default pipeline that you use, and in the default pipeline, the OpenGL does whatever the current model view transformation matrix is. It multiplies your vertices with that. So it looks at the current OpenGL state and just runs the default pipeline with default programs in the GPU. And for fragments, you can do additional operations and interpolated values. You can do thresholding to get some kind of a cartoonish feeling. You can access the texture, make texture lookup queries to find your texture color. You can blend your texture color with the computed color differently, so you can do different things. And I mean, this is per fragment gives you a lot of flexibility on whatever mathematical function you want to have to find the final color of a pixel. You can do it here. You can do, for example, fog simulation, depth of field, blurring of, for example, parts of the scene in which the user's avatar is not looking, or for example, maybe the center is crisp, but the outside, the surroundings may be blurred. You can do things like that. You can sum up colors. You can do per fragment lighting. This is also called fog shading in comparison to Gouraud shading. In fog shading, we use interpolated normal vectors to run the basic illumination model. The diffuse ambient specular, ambient diffuse specular is computed per fragment. You can do that. You can do a color table lookup, convolution. There are different things. I mean, all these is really bound by user imagination. You can do many different things. And it's the GPUs provide you big parallelism. The shader source codes are read by the CPU program. They're given to OpenGL for compilation. They're compiled, linked, and attached to programs, and they execute on the GPU at drawing time. So they're not programs compiled on the CPU. Actually, it's read by the CPU program, but yeah, the OpenGL compiles and stores them on the GPU. And a shader executes simultaneously. The parallelization is done automatically by the GPU by using its available cores are used to do in vertex processing. The vertex data comes in parallel to this single vertex shader that you have provided. So in that sense, it's a single instruction, multiple data type of parallelism. because we have a single vertex shader that runs at the moment. You can have multiple vertex shaders, but usually without loss of generality, you can still imagine that you may have multiple vertex shaders, but a single vertex shader usually is not written for a single vertex. It runs on a set of vertices, and in that sense, those set of vertices are comprise the data of that single vertex shader. There are different languages for programmable shaders. There's HLSL, which is developed by Microsoft. It's the acronym for High Level Shading Language, and it's supported by DirectX 8 and later versions. There is CENG, which is authored by NVIDIA, and there is GLSL, which is closely tied to OpenGL. This Kronos group is responsible for determining the OpenGL specification. So GLSL language is also designed by them. And it's a self-sponsored group of industry affiliates from different vendors, different companies. NVIDIA also is part of this, Intel, Apple, AMD. So we are going to be focusing on GLSL in our class. And here's an example vertex processor. So what can a vertex processor do? So in all these shaders, what they do, they have a set of inputs, and they have some outputs that they need to provide. Some of these outputs are very important must outputs that are expected of a vertex processor. Some of them are optional outputs that, for example, certain attributes, you don't need to, a vertex processor may not need to always provide a texture coordinate output if you're not doing texture mapping. But at the minimum, a vertex processor should provide vertex coordinates, compute or transform some vertex coordinates, and that's one of its main output. In later versions of GLSL, even these default outputs that they should provide, it's not no longer they have default variable names. They are indicated by the modifier keywords in and out. So in indicates as an input variable to the vertex. Out variables, there can be different channels, different number of outputs a vertex processor provides, and each of them should be specified by this output at modifier variable. But for simplicity, the examples we're going to show you here today are going to be using these earlier versions of GLSL, in which you can use these default built-in variables like GL vertex position, or if you look at some of the vertex shaders here, yeah, if you look at this, GL position. So this GL position is at the minimum, a vertex shader should assign some value to this GL position, which is the output of a vertex shader. So this is in the GLSL version 120. And for the assignment, which your assistant is going to make announcements maybe in a couple of days, your last assignment, you will be writing a simple application that uses that implements some vertex and fragment shaders, and in that you're free to use any version of GLSL. So you can actually just use these examples as templates, and also use these built-in variables that we have here to write your shaders. So these you don't need to use the latest version of GLSL, which is actually more difficult. It's getting more and more difficult from the user's perspective. Everything is like now becoming something, some manual processing the user has to do. Manually, the user has to specify what are the outputs, what are the inputs. I mean, it gives more freedom, more power to the users. I think that's the goal of these newer versions. Otherwise, I don't know why they would want to make programmers' life more difficult. The main thing is, as I said, it gives more power to the programmers. It doesn't need to be just GL position. Okay, so it could be any attribute, any input-output variable. And again, also at the minimum, a fragment shader should assign a fragment color. This GL frag color is the output of a fragment shader. These are the outputs that are given to whatever varying we have here. This texture coordinate, for example, is the interpolated texture coordinate by the rasterizer that is given to this fragment shader as input. While the same variable, which is named texture coordinate, is exactly defined as exactly defined as in the fragment shader. In this case, it's an input variable to this. Again, it's not an input actually. We are assigning it, as you can see. It's not an input variable. We assign a value to this vertex, this texture coordinate, and this assigned value with this varying keyword, it tells the rasterizer to interpolate it automatically across fragments. When we have something uniform, it's again a modifier variable that tells that it shouldn't be interpolated per fragment. It's uniform. It's like a constant across all the fragments. Okay, so let's go over these. So the color, normal, position, texture coordinate, their input, texture data is input, the matrix, transformation matrices, model view, projection, material data, light data. There may be many inputs. Some custom variables may be inputs to us, like you see here. We have some custom variables. This H bar post, V bar post. These are really specific to this example. So you may have custom variables that are defined and sent by the CPU to the vertex processor. There may be per vertex attributes like normal vector. I mean, this color and normal, they are per vertex attributes, but you can have some additional, again, application specific vertex attributes that you may have for vertices. And color may be output. If you do per vertex color computation, per vertex shading, you can actually output color as one of the outputs. GL position, as I said, is at the minimum. You have to specify that. Texture coordinates that are going to be interpolated, that may also be at the output of a vertex processor like this. So they are executed. There's lots of repetition of what I just said, so I'm going to quickly go over this slide. We transform the vertex position using the model view and projection matrices. Normal vectors are transformed differently because we have seen how if we have non-uniform scaling, transformation of normals may be problematic. We should get the inverse of the model view matrix top 3x3 parts and take the transpose of that and use that to transform the normals. I think for this, OpenGL provides a built-in normal matrix that actually does that. GL normal matrix, if you multiply your normals with that, they're going to be transformed correctly. Texture coordinates, lighting computation, or for example, you can do interesting things. Vertex positions may be modified based on texture values. So you can use the texture color value, for example, to indicate like a height map. You can, on the fly, you can have, for example, we had such an assignment a couple of years ago, which was to our geometry data initially was just a flat grid like this, a flat terrain, in which all the vertex coordinates, their xy values are different. So this is the xy plane or xz plane. Let's use this. This is the xz plane, okay? And these are the y coordinates, so this is the y plane. And if you define a grid like this, each of these vertices, okay, you may have triangles for each of these grid cells like this. I'm just showing a couple of them. They have their xyz coordinates, and initially they may all just be some x0z. They may all be at y is equal to 0. What you can do in a vertex shader is, for example, you can read some kind of an image from a file and get some color information on that image. Based on that color, okay, based on this color from the texture, you can assign some positive, or maybe it may be negative if you want to go down at the terrain too. You may assign some value to this y coordinate based on the texture lookup, okay? And this will change the geometry such that the terrain is now not going to be a flat terrain, but it's going to be some with some hills and valleys, so you can have something like that. Actually, I had an interesting video on my YouTube channel about this. Let me quickly show that to you. So it's a funny video, actually. Your channel, so not this one. So it was a very old video. All right, your videos. Yeah, this one. So this was homework 3. Look at this. So this terrain you see here, okay, is actually done exactly like that. This was a flat terrain, and the heights fields that you see here are done by looking at the image color. White color, bright color makes it high, black color makes it low. So based on that, we can actually do this, and we can change the height of this terrain immediately by just click with the click of a mouse button. Look at this. So these are actually, this is from let me not ruin the surprise, but you may have seen it now. This is a face here. It's my face, my photograph. Look at my teeth sticking out with white. They are going upwards, and black parts are down. Now, since I have more whiter hair now, I think it will be more higher now. So this is, as you can see the far plane cutting out here. The part that you see here is cut out. I think, or maybe it's just I have a rectangular screen. Now what I'm going to show is that by the click of a mouse button or a keyboard button, I can actually change the height field by changing the multiplier of this y value finding. It's multiplied by some constant. You can just, with keyboard interaction, you can change this constant value. It may even go negative, in which the face is just going to, it's like going to appear like it's melted. Now this is the flat version, and now the height values are going down. Now dark places are now high, white places are at the bottom. All right, so so you can do this in a vertex shader. Vertex shader allows you to change the position of vertices. In the fragment processing, similarly, the color, texture coordinate, fragment coordinates, which are interpolated coordinates, can be input to the fragment, and the minimum output that it gives us is this fragment color. You can also change the fragment depth, which is that interpolated depth value you have if you want to do different kind of effects, or if you want to modify how the depth of your algorithm works. You can also change the fragment depth on your own, give it a different output. But at the minimum, we give a fragment color as the output. Okay, so this is how a fragment shader looks like. There are more examples. It's executed again once in parallel for each pixel, for each fragment. So a lot of parallelism there. We can do Phong shading by computing color, computing diffuse, ambient, and specular for each fragment. We can again fetch texture color and blend it with this computed color. Fog, blur, depth of view, blurring, or different other effects could be established by with the fragment shader. We can also, for example, kill fragments. Their depth values can be altered. Killing a fragment means maybe just not displaying it, just like backface culling. You can have a fragment ignored by the other fragments. For example, if you have like kind of an occlusion culling, killing a fragment will make fragments that are in front of it will be, or behind it, will be displayed. There are many post-processing effects can be applied here. For example, we can do shadows. There's a nice shadow mapping examples we can do. Let me show you another example here at this point, which is this terrain visibility. So is it, yeah, terrain visibility. I think I should have compile command somewhere here. No, let me get it from here. This texture example, how to compile. Yeah, let me copy this one. And the name of the, so it's named terrain. So terrain.c. Let me try to show you this one. I forgot the interaction keyboard mappings, but let's see. So it compiled with no problem when we run it. Oh, we got an error, or maybe it's reading. Yeah, yes. Also, what happened? I think there are some version-related problems that I have here, because the terrain doesn't show nicely. Maybe there may be some non-backward compatibility that the terrain program was working before, but I cannot see my terrain. There is a problem definitely here. Okay, so it shouldn't display like this. There should be a terrain that we see here, and the part that, so this is like a camera that is pointing this way, and with a different camera, which we are here right now, as you can see, we actually see on the terrain the parts that this camera sees on the terrain. So for example, if there are hills and valleys that this a camera located here does not see, it should appear nicely here. So there's definitely a problem with some kind of a versioning, or maybe the height field was not read correctly. No, but I think there's definitely something going wrong about our shaders. And we didn't get any compile error from the shaders, so I think there's a version problem that is going on with this graphics cards. So sorry I couldn't show you that example, but yeah, there are really, now maybe on your machine it may work correctly, or it's difficult to figure out. I have to spend some time to figure out what this interesting error is caused by, but I'm definitely sure it's about some versioning problem with this graphics card. So there are different effects that we can do. So how do we activate a shader? So these are now some code-related API reference manual type kind of slides we are going to have here. I'm going to quickly go over them. The example programs have all these codes in them. This is like a nice explanation of what each piece of code does. So in order to activate a shader, we have to first create a program. Tell OpenGL this create program gives us again an integer handle so that we can refer to these programs. As I said, program is a sequence of shaders which makes up our forward rendering pipeline, is called a program. First we need to create a program. This will tell OpenGL that give us a handle that we will be able to refer to later. And then we create vertex and fragment shaders again, which are just integer handles to us. But with this handle, we say that we may refer to a particular vertex shader in which we attach a program, which is attached to a program. Here we provide the shader source. Here this shader ID is the one that is generated by create shader. So we give its ID here, which is an unsigned integer, and provide a text, a constant character array, which has the source code, the GLSL source code here. So what you usually have is you read a file, you read from this GLSL code that you have, you put it into this large character array, and you give it as the second parameter to this shader source function. And after you have the shader sources, you'd say you may now compile the shader referred to by this vertex shader ID. If there are compile errors, they are going to be here written in compile status. One thing that is interesting is that when there are compile errors, it does not provide a runtime, it does not cause a runtime error on the CPU program. When we have a compile error, if you have, for example, some kind of a typo or a syntax error in a compile shader, in a shader program, when we have an error, your program automatically reverts back to the default pipeline. So it will keep running, your application will be running, but with the default pipeline in place. Okay, so it doesn't, your program does not crash when you have a compile error. And these compile messages usually are, you can get those compile messages in your program, and you can print them out with additional code. For example, let's see how I did that here in spheres.c. When I so this is the print program info log. Okay, so when we attach them, again, every time when I say print program info log, this is the function that I have here in my program. It's not an OpenGL function call. So loading a shader. This load shader is again a program that we have here. So it is a function that I have here. If you look at how load shader works, so same GL shader source, we give it the this character pointer, we compile it, and after we compile it, we can get the compiler output to us by using GL get shader info log, which is going to be put into some kind of buffer, and we can which is this buffer. This error is our buffer, as you can. Error, I think, is a character array of 1000 characters. And this is what I print, as you can see, as compile status. If there was any error in compiling the shader, it would print this in that log. Okay, but as I said, it doesn't cause any runtime error on the CPU application. The application will keep running. We can actually see an example here in texture example. Let me go back to the texture example. So this was the texture example in which we modified it. Now it's not a very good scanning bar. Now let's try to get this back to this nice using the exponential, the specular exponent type of reduction. So I don't need to compile it again, because this GLSL code that I have here is loaded and compiled in runtime by this CPU application. As you can see, without recompiling my program, I now have a better application of this fragment shader. Now, if I have an error, for example, if I have some code here in this fragment shader, which is just garbage, let me save it. Let me run it again and see what happens. Okay, here the compile status gave me this error, syntax error, unexpected reserved word if expecting. So it's not it's interesting. It's not very informative, this error message. It was just the garbage that I wrote, but does it contain something like an if? No, it's interesting. Now before if, so it's so it's really just before this if statement, there's some syntax error. So it's basically what's saying. This is, I think it's telling me, was it the line number? No, it's not even telling me the line number. Okay, so but the result was our application is still running, but I don't see a thing. It's just black screen. So when it runs the default pipeline, I think in this default pipeline, since I don't have any texture mapping done in the application part in the default way, it cannot display anything. It's just this black screen. Okay, but the application did not crash, just didn't give us any correct output. Let's get back to this one. And again, I just save the GLSL, and without recompiling my application on the CPU side, I can get my fragment shader running correctly. After we compile our shaders, we attach each shader to some particular program that we have created, and then we link the program. This is make it as something executable on the GPU. And whenever you say GL use program ID, we activate that programmable shader containing program that we had written. And at the same in a same loop, rendering loop, you can have multiple different programs that are active at different parts of rendering the stage. As I said, you can, for example, render one part of your scene or certain objects in your scene in color, while you can render a single object by activating a different shader, which has, for example, some grayscale non-photorealistic rendering. You can render only that object with this different effect, grayscale non-photorealistic, by just writing GL use program before the call to draw that particular object. So you can switch back and forth between different programs. Yeah, that's actually saying the same thing. It's possible to draw different models using different shader programs. Yeah, this is that example. GL use program, program 1, we draw this bunny, and we activate the different. They look actually similar in terms of style, right? I mean, maybe this is not shaded. Oh, this is flat shading. This is maybe. Oh, this also looks flat shading. I don't know. I mean, if this was completely wireframe and this was not wireframe, that would be a better example to show the difference between them. You can have a color model here and a non-color grayscale model with different programs. And once the program is activated, certain operations, I mean, if you write a vertex shader, you're responsible. You have to replace everything the previous vertex shader does. I mean, the important stuff, the minimum necessary stuff that the vertex shader does, it has to be replaced by your program. It's not like when you override the vertex shader, you are responsible for all the things the vertex shader was doing. Okay, so the install program replaces the all OpenGL fixed functionality. And the way we communicate shaders, when this part is from this dotted line, the left part is the CPU side, the right part is the GPU side. There is this OpenGL application. Our program is running on the CPU, and it can send and receive data from memory buffers. It can send uniform variables. We can, by using this GL uniform function from the OpenGL site at every frame, we can send variables like this hbar post and vbar post. They are actually sent as changing values at every frame to the GPU side. So GPU side shader program, the GPU side may receive variables from the OpenGL program, and the shader program itself, within itself, there's communication between vertex and fragment shaders. Anything that is declared as varying, or in the newer version of GLSL, anything declared as out variable in the vertex shader will be an input variable in the fragment shader, which is going to be interpolated. And they can interact with memory buffers also. These memory buffers may contain like accessing texture memory and other stuff. So this is a crude overview of the communication between these things. So the uniform, and this is the rest of the slides are explanation of how this is done. We can send data with the uniform variables. Vertex shader can send data to fragment shader, but there's no, the pipeline has a fixed direction from vertex shader to fragment shader, from vertex processing, rasterization, fragment processor, and the frame buffer, the final thing. So data flow is one way. You cannot send input from fragment to vertex shader. And to do certain things, you're always writing code that is local to a vertex or local to a fragment. You cannot get information from the neighborhood fragment, for example, but you can query things. I mean, it's really, when you're writing code for shaders, you really have to think locally for per vertex or per fragment. Okay, so that may be challenging for certain types of applications. Yeah, there are uniform parameters that are like global variables, attributes that are per vertex. Attributes are per vertex values, and varying parameters are the ones that are interpolated for fragments. So this is also a nice visualization of how the relationship between those. And here are some different shader examples. As an example, vertex shader, in which modeling, viewing, projection matrix, we get it from the OpenGL site as uniform variables from the CPU. CPU sends these values to us at every frame. And the first line of a shader usually contains a version string to impose GLSL version on the GPU. to avoid these compatibility issues actually. And within the shader, there is just like C, we have a main function in which this GL vertex is a built-in variable that are the attribute variables fetched from buffers. GL normal, GL vertex, these are all our normal and vertex values. We can multiply them with modeling matrices to get some other, like this frag world position. It's just by just multiplying with the modeling matrix. It's still in the world coordinate system, not camera coordinate system. And specifying them as varying says that we are going to be using them for fragment shaders in an interpolated manner. Here's a example fragment shader. We can have these variables that we have here, local variables, a uniform variable that we get again from the CPU side. These varying variables, now they are sent to us as input from the vertex shader, and they are interpolated. And in this case, we can use these normal, the local variables as we like. We can compute other vectors from them. We can this is a computation of actually basic illumination model. This is the Phong shader in which we do lighting per fragment by using the interpolated normal. So this frag world normal comes to us in an interpolated manner. We normalize it, we find the half vector, we take the dot product of that to find diffuse, specular, and ambient, and finally set the GL frag color. When we are making these, setting the values of these uniforms in our CPU programs, by the way, we're out of time. So let me stop here, and we are going to continue, finish this in the first hour on Tuesday. But the remaining part is just these are already existing in our example programs, and it's like an API reference. You can also go over them quickly on your own. I talked about Phong shading or odd shading, and there are some examples of that, how it changes the way we look at this Utah teapot. And there are some other gallery, and there are some resources at the end of the slides to help you get started learning GLSL. Okay, so I'm going to go over the last couple of slides on Tuesday and finish that in the first 10 minutes probably on Tuesday. But that's it from me for today. Let me know if you have any questions. If not, you may also... Oh, yeah, you can ask anything about the second assignment. Go ahead. Let me stop recording at this point.